In my previous live stream, what I did is I vibe coded a new element into OpenSees. What this means is we used Claude AI to come up with a new element that does not exist in OpenSees, come up with a code for that. And we went through the whole painful process, or kind of painful, of implementing this element into OpenSees. So if you want to see that stream, it's available. What I want to do now is I want to do a little recap video, show what the AI implemented. I'm not going to go through the interface. I'm just going to go through the source code and explain what it's doing. Okay, so let's dive into it. Let's dive into it. So here we are. This is the state at which the last stream ended. And you can see here the session with Claude. Let's create a new non-existing element for OpenSees. It should not be available, yada, yada. And at first it went for a thermal mechanical element, but then I asked it to do something more mechanical and it did something pretty cool. It's a sliding hinge element. So the idea is it's a hinge that slides. Basically, it's kind of supported, and so it can have friction. And it can also have a constitutive, a uniaxial constitutive to model the moment at the hinge. Anyway, those details are not important, but what is important is that the AI gave me SlidingElement.h, SlidingElement.cpp, and a test case for this. So what I wanted to do is I wanted to start with a test. Let's review that, did I say VO? That file to see, to get a feel for what the AI is trying to do. So here's a little test case. Feel free to pause if you need to read some of the things. I'll make the font a little bit larger for your viewing experience. So it's going to be a 3 degree of freedom model in 2D, and we're going to set up 6 nodes. So one is at 0, 0, the other one is at 6,000 whatever units towards X direction, and then we have a third one 3,000 units, might be millimeters in the vertical direction, and then we have a 4 in, so it's kind of completing a little square. And then the beam nodes separated for sliding hinge connections 0 and 3. So this duplicates the node at node 3, and then node 6 duplicates the node that is at 4. It's fixing the base nodes, and it's creating elastic material, and then it's going to have elastic beam column between nodes 1 and 3, and then 2 and 4, and 5 and 6. So here's what it's doing. Let's try to do a little drawing. Let's bring up Inta from the Omachi menu. Let's should be able to, no, this isn't the terminal window. This, was that the shortcut? No, that's not the shortcut. Come on, man. Okay, let's widen it up. So it's creating, that's really bad. It's creating a node 1, I think node 2, like this. Let's bring that out. So node 1 and node 2. Node 2 is at the, undo. So this is 1, this is 2, this is 3, and this is 4. 3 and 4, that's right. This is 3,000 units, and this is 6,000 units. So it was incentivized to do something for bridges, and it's going to be not as cool as other people drawing on this. So it has a column here. Let's use another color for that, green, yucky green. So column, this is this call over here, and then elastic beam column. It's going to have a beam connecting nodes 5 and 6. So it's up here. And what's 5 and 6? 5 and 6 are nodes over here. You can think of them as nodes that are directly on top of 3 and 4 because they're duplicated. And these nodes over here are going to be, are the nodes that belong to this beam. So actually, these ones over here are 5 and 6. Let's go for the eraser. This is not a thing. This is not a thing. This is looking disgusting. Anyway, So these top nodes are going to be joined with the bottom nodes by this new element. That's the idea, 6. So I can draw in blue here, connecting is going to be this new sliding hinge element. Let's add some text here. Sliding hinge element. And the same thing for this other node over here, or the other element that's going to join these all together. So we can see that's what's going on. Elements 4 and 5 are going to connect elements nodes 3 and 5, and then 4 and 6 for element 5. So this is kind of the setup. And then what is it doing? It's at load 3. At load 3, it's adding a horizontal load, like so. It's going to load, and then a vertical load at mid-span of the beam. What? Load at node 5? That's not the mid-span. You don't know how to OpenSees. It was supposed to do it here, but this is not how you add a load at the mid-span. Anyway, a little hallucination here. Don't vibe code, people. Don't vibe code. And then it's going to ask for some output. So recorder, the node displacement, that's kind of standard for nodes 3 and 5. And then column forces, beam forces, a lot of stuff. And then kind of standard analysis options is doing a load control analysis, and I suspect it's going to do 100 step of those. There we go. So that's what's going on. And then cyclic, it goes into cyclic. So first it adds the vertical load, and for some strange reason, it's adding a horizontal load to induce sliding. Why? Okay, the way you would do this is you would actually first load downwards, apply self-weight, and then do something sideways. But okay, this is only useful like to set up something that you can use later to do what you really want to do. But the format is nice, and it has everything that you would need anyway. And then it goes into some cyclic stuff, I think. So let's go down here, setting up analysis. Cyclic analysis. So it's adding other side of sliding interface, recreate model. Oh, so it's recreating the model. So I wonder if the static part works, then the cyclic part might not work. So it recreates everything. And now what it does, where does it add loads? Yeah, just this one, cyclic load pattern. But the load pattern, it's taking a linear. This is not cyclic. Okay, so it's all over the place. This doesn't make any sense, but it doesn't matter. What I want to go and do now is explain what it did with this element. Let's keep this figure over here, and let's bring this down. Okay, so the sliding element, let's go for the sliding element H, the header file. So this is fairly standard for an OpenSees element. You're importing element, matrix vector, and integer data. Integer data is a vector of integers, basically. And then some forward declarations. Why it's declaring node? It's declaring node because, well, it doesn't actually need the header for the full header. So I guess this is fine. At this point, it only needs to know that, for example, some of these functions are going to return pointers to nodes. And that's all it needs to know. It doesn't need to import the full header. But you'll see other elements, instead of doing this class node, they'll import the node header, the full node header. At this point, it actually makes more sense what Claude is doing. The same for the material, channel. Yeah, for defining the header, you could use these forward declarations. It would be actually nicer because you can see that it's not being used any further than just stating that these are classes that are going to be defined elsewhere. When we get to the implementation, those are definitely going to be imported because we're going to be using functions. Okay, so I discussed a little bit of this in that live stream, but this is the 2D constructor. It takes a tag, 2 nodes, a uniaxial material that represents the hinge resisting force, and then a friction coefficient for the sliding direction, and a normal force. The normal force, yeah, this is weird about this element. Like, what's the normal force for this element? Right? It should be able to have another element that would provide the stiffness in that direction and compute the normal force from that. Okay, that's weird. Sliding limit. So I guess what it's going for is this thing will slide until it hits whatever this limit is. I guess it's set to infinity right now, but you can set this to something else. And if it slides, the deck, you can imagine the deck sliding until it reaches some sort of abutment at the end, or some sort of element that will restrict the sliding in this direction. So the element will go stiff once we reach that point. And then a gap, initial gap. What's that gap needed for? What kind of gap? I don't know. So does friction activate after what's the difference between the sliding limit and the gap? Okay, that doesn't matter. We're trying to make sense of something that a robot wrote. So what I want to focus is on the interface. Okay, and then you can see the stuff that OpenSees requires from us. You can see get number of external nodes, that returns an integer. So if we go over to let's clean up everything over here. So if we go over to the implementation, we will see, for example, that function get number. So it was get number of external nodes. Get number of external nodes returns 2, because this element connects 2 nodes. And then you can ask for the external nodes. What that'll do is it'll return the integer data list that contains the 2 nodes. So when the constructor gets called, you get 2 nodes coming in, and then in the constructor, the data member, so down here, all the way down here, we should have an integer data variable called external nodes, contains the tags of the 2 nodes. This needs to get filled up in the constructor, probably. So if we go here and we take a look at the constructor, the 2D constructor, this is the first one, node 1, node 2, you'll see external nodes getting filled in there. Also, the data member external nodes over here is specified with a slide 2. So you need to initialize that variable first. So it gets initialized here in the initializer list. And then we go down to external nodes and we fill that up. The same kind of happens with other initial variables. So for example, for some reason it has the one with the numdof. This is actually not needed as an internal variable. Is it here? Yeah, that integer over here, the number of degrees of freedom. We know it can all, okay, no, because we don't know because it's 2D or 3D. So in the 2D case, here we go. In the 2D case, numdof is set to 6 because we have 2 nodes and 3 degrees of freedom per node. That's 6. But in the 3D case, we should have more. We have a constructor for the 3D case. Do we have a constructor for the 3D case? I am not seeing it. But it's declared, right? It is declared. Sliding there, 3D. Let's take a look. Let's see if I can find it. So colon, sliding hinge, sliding like this, and find the next. That's the only one. How did this code compile? How did it compile? It shouldn't compile because I'm declaring sliding hinge element over here with 6 degrees of freedom. So I guess this is never getting called, and that's why we can compile it, because I'm not seeing the implementation for the 3D case. But that implementation would actually have number of degrees of freedom would be, yeah, 6 per node, right? In this case, it's 3 per node, 6 per node, 12. It's just like a beam, but it's not implemented. Bad, Claude. You didn't implement it. So let's go through the rest of the functions that need to be defined. So that was get external nodes. Get external nodes, then as I mentioned, returns that list. And then the node pointers. The node pointers returns an array of pointers. So this is this one, this array of pointers over here. And that also gets populated. No, it does not also get populated. It gets populated when in the call to set domain. So after the element is set up, we call set domain with the domain. And what happens inside this function, you can see we extract the node numbers, and then we ask the domain to give us pointers to the nodes. This is pretty standard. So node 1, store that in the first component of the array, and the node 2 in the second component of the array. Check if either of those are 0, in the case are null pointers. And that's it, we've set up the pointers. We need those pointers then to get the displacements and other things, other interactions with the domain. And then we call set domain for the base class. And then what is this doing? It's doing a quick check if the nodes that we've defined that have the correct number of degrees of freedom. So we need 3 degrees of freedom per node. If that's not the case, we'll return an error, and this will probably fail very ungracefully. Okay, here we go. We keep going. So that's the node pointers. Get number of DOFs. Let's go back up. Number of DOFs. Numdof. That's 6 in the 2D case. That's pretty straightforward. We already discussed set domain, so that was part of what I need to do. And then these are more specific functions that's going to depend on what your element is doing. Like from here on, it's something that we need to know what the physics is that we're trying to do. So let's just quickly see a few of these. Let's go in implementation order. So first of all, the internal variables related to the state of the element. That's probably the sliding displacement, sliding velocities, trial rotation. These are physical internal variables that once the global analysis has converged, we store them in committed version. So in the header file, you'll see that the internal state variables, we have trial internal state variables. Those are used during iteration to achieve convergence. And then the commit versions of those internal variables, those are only updated once the global integrator has achieved convergence. And then I guess it has some working variables that it's using. And then what comes is matrices and vectors to report stuff out. So these are the main state variables that Claude came up for this element. And then these are some variables. I don't know what they're doing. So commit state, what it does, it takes the trial version of the internal variables, and then it saves them in the commit displacement. It's also calling the material. So remember, one of the inputs to this element, one of the inputs is a uniaxial material. So it takes a pointer or a reference actually to the moment material. So let's take a look at the example real quick. The example, let's go over to the top. It generates a uniaxial material, steel 1, and it's going to use that, I guess, for this element. So you can see that that is the material that has tag 1, and that's our 4th parameter in the sliding hinge element. So the first is the tag, node 1, node 2, and then it's feeding this uniaxial material tag into as the material that's being used by the new hinge. So let's see what happens in the OPS in the parser in the parser function, the ones that's reading the tickle. So I don't know where it placed it. Let's take a look here. Search OPS sliding hinge. This one, the one that we use to interface the element into OpenSees. So it's getting a tag. It's getting the nodes, 2 nodes. It's getting the material tag. So this is just an integer. And the the header takes a reference. So we need to get a reference and pass that to the call. So, and then the rest are other parameters. So the fun part is here. We get the uniaxial material. So we're going to use this element API function. Oops. Get uniaxial material with the material tag. And that's going to get us a pointer to the the material that corresponds. From that pointer, we can feed a reference into the constructor over here. So this is actually dereferencing that pointer. So what you get out of this is a reference to the material, which is used by the constructor. There we go. So from there, we can go back. So this is at the end. This is at the end. So we were taking a look at which function? Commit state. So anyway, this this element holds pointers to a material, so it needs to update those two. Let's go back to commit state. Commit state. There, that's the function. So we were here. So because this hinge holds materials inside, we need to call their commit state too. And that gets done here. That's good. We can revert. Revert will do the opposite. We'll call the revert function on the materials, and we'll take the last commented variable and set it to the trial functions in case something happens, the analysis doesn't converge. This gets called. And revert to start just makes everything the initial value. Then update. The update function gets called once the displacements for the current trial iteration have been set. So this is supposed to update all the physics inside the element. It's going to come up with a new trial variable. So you can see it's reading the trial displacement from the nodes, from the node pointers. This is why we need pointers to those nodes. And it's calculating some stuff, relative displacements, yada, 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 yada. And here it's updating a trial displacement variable, and then it's calling an update sliding function, which basically just sticks all this code over here. For some reason, it made sense to Claude to separate this part. But what I'm looking for here is the update of the trial slide displacement. That if everything converges, then this variable goes to the commit. So that's kind of how it goes. All these internal variables, the trial versions are getting computed, and then when the commit gets called, those gets saved in the commit version of those functions. Get tangent stiffness. This one does exactly what you think it does. It computes a stiffness matrix, and it's going to return a reference to a stiffness matrix. So you can see K is equal to 0. It's important here. We're using this technique where the stiffness matrix is being declared here as a matrix pointer, a pointer to a matrix, and where's that getting initialized? So that should be getting initialized as soon as we know the size of the stiffness matrix. So probably here in the constructor. Here we go. Here where we allocate the memory for the stiffness matrix. So as soon as we know the size of the number of doves, the num.dov, we can initialize these the stiffness matrix, some sort of residual, and P. There's no mass matrix, but if you had a mass matrix, you would do it here, and then finally you set them to 0. Okay, so when we go to the function called get tangent stiffness, the first thing we do is we zero that out so that we don't have anything inside here. That kind of makes sense. A little optimization that you can do here is declare it static, and that way you'll have to only allocate once. But it's going to depend on whether your element is 2D or 3D anyway. So we update and we do some computations here to fill out the terms of that stiffness matrix. And then we return a reference to that stiffness matrix, return a reference. So we need to dereference that pointer before we return. That's cool. Get the initial stiff is the same thing. We're going to use the same matrix. We just compute an initial stiffness and return a reference to that. And then get mass matrix. In the case of the mass matrix, we set K to 0 and we return K. And that's just it. Zero mass. but we could do some stuff there. Get the damping, 0 damping, that's fun. 0 the load, in case we have load. This element is not implementing any loads, any element specific loads. Some elements have loads. For example, we can go to why not 10 node tetrahedron. That's an element I implemented. Oh, but we need to go to the implementation. Node tetrahedron, sorry, not this one. 10 node tetrahedron CPP, and let's search for add load. So add load, actually, you can add brick self-weight or self-weight loads to this element. Brick, because it's reusing some old code there, so that's probably not a good way to go about it. Anyway, this element does not implement element-specific loads, and because it doesn't have a mass, it doesn't do anything when you add inertia to unbalance. So in dynamics, it works the same as in statics. And then in get resisting force, this one gets called to form the global residual. It does some computation. You have the resisting force, R, is set to 0. You compute some stuff, and then you return a reference to that vector you just computed. Remember, this one was also set up in the constructor. So all the way up here in the constructor, we set up R, and then we also set up P. What is P? I don't remember what was P, but we should know. Element load vector. Yeah, we're not doing an element load, so this is not being used. So where were we? We were get mass, get load, add load, get resisting force, and then resisting force including inertia. This is a good pattern. Once you just call get resisting force, but here you have the opportunity to include inertia. So I remember there was something. Let's close this. Let's close that. There was something here. Yes, this thing, resisting force including inertia. Add inertia load to unbalance. So it came up with a little function that added the inertia load, but then it's not being used. So let's search for that. Add inertia load to unbalance. There we go. That one is 0. Get resisting force and get resisting force including inertia. So theoretically, what we could do here is we could get resisting force, for example, something like that. This returns R. So this would fill out R. I'm calling this one. So just this call would fill up R. We don't need to catch the variable that comes out. And then we could say add inertial load to unbalance. We could call that function, which is defined a little bit up here. It returns an int, so we need to do nothing. But in here, we could take R and do something like plus equal add inertial loads. So for example, it could be mass times acceleration. Minus mass times acceleration. So you would need to get the acceleration at the nodes before you do this. Okay, let's go over here and comment this out. It doesn't make any sense. But this is where you get a chance to add those inertial forces. Sense self, not implemented for brevity. Come on, Claude. You lazy clanker. But what these functions would do is they would send all the variables that are needed to specify the state of the element. So probably all of this plus wherever the parameters are stored. Bool sliding. Probably this plus this. All needs to get sent to other elements, and then you need to specify how to receive them. So for example, back in the 10 node tetrahedron implementation, we can take a look here at the send self. And you can see here, this implementation, what it's doing is sending a bunch of stuff. So it's using the channel The channel is one of the input arguments to this function. You can also add a comment tag that helps MPI figure out or match the messages, or all. It's mostly used for the database. Anyway, that comment tag, you can see that it's taking some integer data. There's integer data of size 27, and then I'm filling out that integer data all the way up to 26. And once that is filled out, I use the channel to send that integer data that gets sent. And then there's some other thing that receives this. This could be a database, or it could be this receive function, which is called later. So you can see the receive function has a static integer data of size 27. And the first thing that one does is receive the integer data as a vector with this channel function. And then what happens is we unpack that data. So this data gets placed into variables that correspond. That's kind of the anatomy of the send and receive self functions. If you have questions about those, feel free to ask. There's a handy little print function here that you can use to print the state of the element. And then the set response, these handle the output. So for example, in this case, when I request a response from the element, so element type force, it's going to go here and it's going to say, I'm trying to get a force response, and I'm going to define that force response to be element response with a tag of 1. So then when the get response gets called, so this is just to set up tell OpenSees what type of outputs are defined and what the size of them are. So basically here the data type of this input will tell OpenSees what the size of this output is, and then it can go ahead and get it. So in the case of 1, it's going to get the forces, and it's going to set a vector with the resisting forces. In the case of rotation, for example, if we take a look at this other case, the rotation response would be response number 3, and you output the trial rotation. Trial rotation is this variable over here, this vector, which should have size 2, I think. Let's take a look real quick. All the way up here in the constructor where we define what trial rotation is. Trial rotation, has a size 1, so it's a relative rotation. Okay. So that's the one over here. And that one is set over here in the trial rotation. That's where we are. And you can get more stuff, and that's pretty much the pattern. Displays self, I haven't seen this one implemented. There's supposed to be some renderer. I don't know how to use it. So you can skip it, or you can implement it by looking at other OpenSees elements that do implement it. And then accessor methods, these are probably used in the element implementation. So I won't go over these. These are internal to the new element class. And then the implementation finishes with the interface function. So this one reads the tickle again and outputs the element pointer. So that's the anatomy. That's the anatomy of an element in OpenSees. These are all the things you need to implement. And this is a working implementation for this. It's not the implementation works as far as it compiles, but it does not work as an element. We need to develop it more, come up with a real test case, and check with some theory. So this is just a toy example. If you want these files, I'll leave them at the comment section below with links to these files, and so you can take a look at what's going on. And you can see that other stream where we went through the whole vibe coding process, so you can see what needed to happen for this to get implemented into OpenSees and correctly interfaced, so that we get to the point where we can call it from Tickle, just like we have here. Maybe I'll do another video on how to call this from Python, but that's really trivial once you get from this place. Tell me if you're interested in that. And yeah, I'll see you guys next time.